Okay, welcome back, everybody. So we were taking care of this stuff, and sorry, you might see this little statement here. One of our classmates was mentioning how they didn't quite understand the E thing, and I just wanted to reiterate one more time that because this is going to come up a lot. E is going to be a number that shows up forever. It's one of the most important mathematical numbers in all of existence, as I was kind of gushing about it a little bit. But so when you see this e to the 2e to the x plus 2 minus 3, that's really no different than saying like 2 times pi raised to the x plus 2 minus 3. Pi is just a number. E is just a number. I know, like, I wish we had chosen something else to make sure that it was like not one of the letters of our alphabet. Because like pi is a Latin, is a Greek letter. And so maybe we could have gone with epsilon like this. So like maybe it could have been 2 epsilon x plus 2 minus 3. And maybe that would have made it a little bit more intuitive for us that it's a number, it's something new. But epsilon is already used in a lot of proofs and everything. Like basically every analysis proof, every proof about calculus and pre-calculus, it almost always relies on let epsilon be greater than 0. So it's we can't do that, so we use the E. So just as a reminder, though, that the E is just 2.71-ish. So it's no different than any of the other ones. And so if you're plotting it by hand, then you use the approximations. You just plug in the points and plot them with the approximations. But if you're using a graphing program, then you want to use the exact value. So when we plugged in -2, we got e to the 0, which is nice. That's always going to be 1. Anything to the zeroth power is always 1, save for 0 to 0, but that's neither here nor there. So this becomes 2 times 1 minus 3, which is -1, and we got that point. And then if we plug in -1, we get 2e to the first power, but we usually don't write the first power. We usually just write it as, like, we don't write x to the first power, we just write x. So in a similar fashion, we don't write e to the first power, we just write e. And so it's 2e minus 3. So the approximation was 2.44, but on Alex, you'd want to write -1 comma 2e to the 2e minus 3. So we have those two other ones, but I'm going to skip those and go over into app. Oh, yes, go ahead, Ronnie, and then JT.
Plus two, though.
Yes. The in the exponent. Yes. I skipped that step. So there's a preliminary step going on right here that it's going to be. Let me zoom in and use a smaller thing. That this is going to be equal to 2e to the -1 plus 2 minus 3. And that's where I get the e to the 1. Yes. Which then equals that. And similarly here, when I plug in 0, I'm going to get 0 plus 2 in the exponent. And that's why I got 2e squared. Okay. And then we go in. Oh, yeah, JT, sorry.
So are you just putting the 2e minus 3 because it's not like if it was just the answer just ended up being like 4.12 or something, like
Then I would write just 4.12.
is it because the answer is just longer?
It's because it's an irrational number. Like there's a fact that we never actually proved, but it's a useful fact later on, and we don't really we have like mathematicians, they like in their first semester they usually have to prove it that you can never add two rational like an irrational number plus let's call I an irrational number, and I plus any integer like any rational number q, it'll always be irrational. So like square root 2 plus 5 is always irrational. Pi minus 1/2, it's irrational. And what I mean by that is it's a never-ending, non-repeating decimal expansion. So we will never actually be able to write down all the decimals. So anything that we write down that's a finite decimal is going to be an approximation. And that's the reason why. And the frustrating thing, like I'm actually curious about this. That would be an interesting thing to guess is how many decimals do you need to be, how many decimals do you need to write down for Alex to consider it the same? Because they must be like every computer actually uses an approximation. It doesn't have E in its database because E is an approximation. What it actually does, by the way, if you're ever curious how the calculator computes sine, like if you've ever used your calculator, if you're planning on taking 127, you will use this calculator to calculate sine of pi over 6, sine of 32 degrees or whatever. And it gives you an infinite decimal number. It gives you up to like 8 decimals. And if you've ever wondered how it works, it's actually using a very, very powerful concept in calculus. Specifically, you'll see it in Calc 2. And so the same thing happens here with Alex. It doesn't have E in its database because it's an infinite number. It's an infinite decimal expansion. So I'm guessing that if maybe you write like 15 decimal places, it won't actually care. But if you round it to 1 or 2 decimal places, it starts to get really, really angry. Me personally, on an exam, I don't care. You can use an approximation because that's the best thing we got. But Alex can be a little bit finicky. Cool?
So on the test, we can leave it as a decimal, or do you want it to put it in E format?
On an exam, you can use the approximation. You can use the decimal. Absolutely. And so when we you'll see I'll be posting an exam review pretty soon here. Oh, it disconnected me. Let's go back. Let's see. Something wrong? Is it next week? Next Wednesday? Okay, so I'll be posting the exam review pretty shortly. Okay, are you not? Why aren't you screen sharing? There we go. It doesn't want us to do it. Okay, am I just not connected? It's saying that I am. Okay, I'll pause the recording. Fixed. What were we saying? Can't remember. Okay. Just yeah, using your approximations would be good. So we move on to some applications, and I actually think these are very, very useful ones. Like in terms of all the applications we've seen in this course, the word problems, if you will, these ones are probably the most reasonable. I remember like so not these ones. I've used these in finance when I've taught finance. My students have used them quite frequently. You can use this to figure out how much is going to be in your account stuff. There's another one that I used in chemistry quite a bit called radioactive decay. Very, very common. If you plan on taking biology, you might be using exponential models. We won't go over logistic growth, but it is a very, very useful thing. This is honestly, the most common thing. You'd be surprised at how many things in real life can be modeled by exponential growth. So the first ones, because it's all about that dollar bill, right? Is the compound interest formula, which is A is equal to P times 1 plus R divided by N raised to the NT. That is the formula. And it's a pretty intense formula. You do not need to have any of these formulas memorized. I've decided that I'm going to provide these formulas along with the letters and what they mean, so that you don't have to have that memorized. Just know how to use it in the mathematical context. So don't worry about having them memorized. Just know how to work with them. So in this formula, the original names of them are the ones that are the first thing before the slash. So they usually say that A is the total amount and P is the principal amount. But I find that to be really, really confusing because like, what does it mean by total? Is that the total amount that I put into the account, or is that the total amount after I've put things into the account? So I like to call it the future amount. It's the amount that's gonna be in the account after some odd years. P is the principal, but I like to call it the initial amount, the initial amount that has been invested. R is the annual percentage rate, or the APR, in decimal form. It needs to be in decimal form. And I don't think we've talked about that before, but maybe I should add a little note here. To convert percents to decimal form, move decimal point 2 places to the left. So if you have 72.8%, I'll let you write that down before going over this example, just because we haven't really talked about it, but there are 2 different forms of any percent. There is the way that we interpret it when we talk, so that it's under, like, that we can understand it pretty well, and then there's the way we use it in math. Because it's a percentage, it's supposed to be a part of a whole. And so if you say 72.8, that's 728, like if you just say 728, 72.8 without the percentage symbol, that means something a lot different than 72.8%. Because you're saying that's 72.8% of 100. So what we do to convert this to decimal format is you move it 2 places to the left. So it goes whoop, whoop, right there. So the decimal version is 0.728. If I had something like 8.2%, I would move the decimal point 2 places to the left, right there. And so this would become 0.082 as a decimal. So the decimal version is you just move the decimal place 2 units over because it's dividing that number by 100. And one of the cool things about the digit system, the decimal system, is that whenever you multiply or divide by a power of 10, so like 10, 100, 1,000, all it does is move the decimal point by the power. So 10, multiplying by 10, you move the decimal point 1 to the right. Dividing by 10, you move it 1 to the left. Multiplying by 100, you move it 2 to the right. Dividing by 100, which is what we're doing here, you move it 2 to the left, and so on and so forth. So that's a very, very useful thing, especially for these ones. Because if you don't use the decimal form, the numbers get outlandish, and we'll see that in a second. And then there is the continuously compounded interest formula, which is A is equal to PE to the RT. Oh, I didn't even get to finish talking about the N and the T. N is the number of times that the interest is compounded per year. So so just as an aside on this one, monthly implies N equals 12. Weekly, does anybody know how many weeks there are in a year? 52. N equals 52. Quarterly, N would equal 4. Annually, N would equal 1. This is the formula, by the way, that makes sure that the rich stay richer. This is 100%. I was talking to my other class about it. I disagree with the concept of percent-based raises. Percent-based raises are BS. They like to think, oh, we're being fair, we're being fair. 5% of $100,000 is $5,000. So a 5% raise for a person with a $100,000 salary is $5,000. That's significant. Whereas if you're making 30,000, 5% of that is, I don't remember off the top of my head, and I don't want to calculate it. 30,000 is only a 1,500. So like your boss gets a 5% raise and you get a 5% raise. They say a COLA, like if you've heard of the terminology COLA, it means a cost of living adjustment. And a 3% COLA for me is a decent chunk, quote unquote, but a 3% COLA raise for your CEO who makes 3 times as much, or in some cases 30 times as much, a 3% COLA is insane. That's a way bigger, like that gives them so much more money than it does to you. So I don't agree with percent-based raises, and neither should you. It's wrong. It's anti-worker, and it's BS. It's all because we don't know enough math to realize how percentages are unfairly favoring those that have more money. This is a good example of this. But this is just if you were able to put it into an account for just once. But that's not usually how it works. But we'll get to that in a second. So And then T is, of course, time. T is always time. Almost always T is used for time. And when it comes to compound interest, more like financial exponential models, it's always in years. And then the continuous compound interest, you notice that it doesn't have N. And that's because it's infinitely compounded. It's compounded every millisecond of every day, every fraction of a millisecond every day. That's why it's compounded continuously. So N is actually infinity. And one of the cool things is that as N goes to infinity, this whole thing goes to E, which is pretty nuts. But that's a whole different proof. And if you want to know where these formulas come from, I'm happy to show you. But I want to move through them if possible. We have exponential growth and decay models, which is y equals y sub 0 e to the RT, where y is your amount, whatever it may be. So maybe it's exponential growth. Maybe it's like a bacteria population that's growing at a specific rate. Maybe it's some radioactive substance that's growing for whatever reason, or maybe it's got a radioactive decay, in which case you're measuring mass, you're measuring grams or milligrams or whatever it may be. And then y sub 0 or y naught is your initial amount, the starting amount of your compound or whatever it may be. R is your relative rate in decimal form. And if R is greater than 0, it's growth. If R is less than 0, it's decay. And then T is time. This time it could be measured in seconds, could be measured in hours, could be measured in years, could be measured in decades. It's all hard to say. You have to wait for the context of the problem. And then there is population growth, the final one, which is P for population is equal to P sub 0 times 1 plus R raised to the T, where P is the initial population, rounded to the nearest whole number, right? Like I know Charlie Sheen would disagree, but you can't have 2.5 men. You can only have two, and then like maybe you can have one man and a woman who's pregnant in their 20th week pregnancy. I've always wanted somebody to be cheeky and write that on the exam when they get like the approximation. But either way, P sub 0 is the initial population. R is the rate of increase, of course, in decimal form. And then T is in time. So what this is really saying is basically you take your initial population and then you have 100% of your population plus an additional growth rate. Like if they say that your city is growing at 10% per year, then R is 0.1, 0.10, 10%, and so on and so forth. Because each year it will grow by 100 plus 10% of what it was from the previous year. Okay, so let's look at some examples. Isaac invests $3,500 in a savings account at a rate of 8.3% compounded annually. Assuming that no withdrawals are made, find the total amount after 13 years, and then also how much would he make if the savings account was compounded continuously instead. So first and foremost, we've got compounded like it says compounded annually. Compounded annually. That means that n is equal to 1. So with these types of models, we can realize that they are functions of the variables, but you can also just look at them as purely a formula and find all the values. So the formula is A equals P times 1 plus. Let's wait until we write down the things. We have A, we have P, we have R, we have N, and we have T. So do we have A, which is the future or the total amount? Nope, that's what we're trying to find. It says how much will be in the account. How much will be in the account after 13 years? So A is unknown. P is the principal or the initial amount. So that's got to be 3,500. R, one of the best ones. It's very nice and quick to find it because it's the only one that's a percentage. APR stands for annual percentage rate. So it's 8.3%, which we convert by moving the decimal place 2 units over to 0.083. N is the number of times it's compounded per year, which we found to be 1. And T is going to be 13 years. So A is equal to P times 1 plus R divided by N raised to the NT. So right now, if you're looking at this, you'll notice that the only unknown we have is A. So we only have one unknown, which means we can solve for it. And in fact, this is a very quick one because there's no needing to divide or multiply. It's just a straight plug and chug, as the kids say. So this is 3,500 times 1 plus R, which was 0.083, divided by N, which is 1. So you don't even really need to write it, but it's just so we see where we're plugging it in. And then raised to the NT, so 1 times 13. So I'm pretty sure all of us in this class, I think I was looking around, I think all of us do have a Casio that's really, really good, like the good calculators that have math print, meaning that you can like, it's a WYSIWYG thing. What you see is what you get. And so that's good news, but if you don't have it, please be careful. If you have the TI-30 XIIS, that bad calculator, let me know. It's not bad, but if you have that calculator, let me know, and I'm happy to find it for to show you how to plug it in, especially even on the exam. I don't want that to be the reason why you don't get the problem right. So approximately, if you round to the nearest 2 decimal places, you get $9,868.20. And we'll round to we'll round to 2 decimal places because that's what makes sense. Dukes. Thank you. Thank you, Mark. I appreciate that laugh. I knew that was genuine. So that $3,500 grew, let's see here, about $6,000 in interest, which is not bad, but it took 13 years to do it. As an aside, if you used 8.3 instead of 0.083, the number that you'd get for your account is you'd get 1.36 times 10 to the 16th dollars. That's 16 zeros. And so that's pretty sweet. That's a pretty good deal. Pretty good deal if you can get that. Somebody at someone at Wells Fargo definitely messed up. And so don't tell them, just become the next Jeff Bezos and use your money for good. Either way. So like with these ones, especially with word problems and especially in exponential word problems, I always tell my students to reflect afterwards, not reflect on your life and why you're taking mathematics, why you're taking Math 126 at all, but rather reflect to make sure that your answer makes sense. Case in point, we're not going to go over it in this class, but there is a formula called the amortization formula, which is how they calculate your mortgages for houses, if we could ever afford one. And the formula for it is very, very complicated. It's more complicated than this, and it involves this actually. And it's very easy to mess up in your calculator. And so I really wanted my students to like understand, like, listen, you got to check to make sure it makes sense. And every time I taught that course, I would always get at least 1 or 2 students who would get the answer wrong. They'd say like the question was $400,000 house, 30-year mortgage at 4.2%, 4.2%, and with like $400,000 house, how much should your monthly payment be? And they got $41. So I mean, I'd love to see that. Don't tell Fannie Mae. Just keep that on the DL, as the kids say, and just let it go. But you know how it goes. Okay, so make sure this makes sense. That is the first answer. And that's the first part. And then it also asked us to do it compounded continuously. And I'm going to abbreviate continuously to CONT because that takes way too long to write. And that's the A equals PERT formula. So there's no n, but all the other variables are the same. P is still the same. E is just the number E, so it's 2.71-ish. R is still the same. T is still the same. A is still the unknown. So A is equal to P, which was 3,500. E to the R, which is 0.083 times T, which is 13, which approximates to 10,296.08. But I'm not going to box that question. I'm not going to box that answer in because that's not what the question's asking. Always reflect on the problem and make sure you're answering what it's asking for. The second part of the question is saying how much more would be in the savings account if it was compounded continuously. So how much more? We'll take our new amount, 10,296.08, and we'll subtract off the amount when it was compounded annually, $9,868.20, and you get approximately $427.88 more. So the point being of that part of the problem is to show you that the more times you compound interest during the year, the more it gains in interest. If it's the same account but compounded differently, then you will make more money. But there's always stipulations of these when you look at accounts at a bank. If they're trying to give you you're trying to choose like a CD, not a compact disc, but a I forget what the name of it is for this, what a CD is at a bank. What is that name called? Let me know. It's like it's an account that you don't want to you can't touch. Like you give them money and then they're investing it and they're like it's growing money or whatever. They'll usually give you a bunch of different rates and along with a bunch of different year amounts and a bunch of different APRs. And so what you want to do in those situations is compare and contrast them. There's actually calculators that help you find this stuff out. But point being is that the more times you compound it per year, that allows more interest to accumulate. So every single time, so if it's compounded monthly, each month it gets a little more interest each month instead of just only being compounded once per year. Okay. Any questions on that? The delightful town of Orgrimmar, I just thought of that name organically. I've never seen that name in any video game or anything like that. But Orgrimmar is a delightful town with a population of 32,180 people, or orcs maybe, or trolls, and is growing at a rate of 2.65% per year. If this rate continues, how many people will live in Orgrimmar in 5 years? So this is a population model. So we're going to be using P equals P sub 0 times 1 plus R raised to the T. And with me, by the way, on an exam, if you identify the correct model, that's usually worth at least 1 or 2 points of partial credit. So getting that part right is like even just writing down the equation. If you don't know where to go from there, you can at least get 1 or 2 points by knowing which formula you need to use. And so now we just need to identify things. Do we know P? P sub 0, R, and T. Do we know P? Nope, that's going to be the future amount. How many people will live in Orgrimmar in 5 years? So P is the unknown here. P sub 0, that's going to be the initial population from our model, which would be 32,180. R is 2.65%, which converts to 0.0265 because we move it 2 decimal places over. And then T, it's asking after 5 years, so T is equal to 5. Any questions so far? And once again, it's going to be a straight plug and chug. P is equal to P naught, which is 32,180 times 1 plus r as a decimal, so 0.0265 raised to the t, which is 5, which equals 36,675.9024. And we want to round to the nearest person because we can't just, so like, technically speaking, we should round down because this, like, we should always round down because you can't, like, that person isn't being made yet. That 0.9 is not real. So technically speaking, but Alex and the convention is to round up. So approximate, like, round like normal means is what I mean to say. So round to since the decimal is above 5, we'll round up to 36,676 people. Or 36,675 people with one pregnant. And then so 0.9, it's 40 weeks is a typical pregnancy. So for like 0.9%, 0.9024 times 12 is 10, no, not 12. What am I doing? Not 12, 40. One person pregnant in 36th week, if you want to be really cheeky. Yes, JT and then Ronnie.
And then the answer,
Yes.
that have counted instead of putting the answer and then people.
Oh yeah, like since it's like
It's supposed to be like mean population.
exactly since the formula, like especially since I'll be giving you these formulas along with the name, like what the variables mean, it is assumed that you can just box in the answer. We know the context of that thing, and if anybody has any problem with that in your future math courses, let me know, and I will come to your aid. I will actually write. I will happily write a letter saying, like, if you send me a picture of the of the problem and why you got marked down, I will happily argue for you. So, Ronnie, sub-zero just means initial. Usually, when we see p sub zero or y sub zero, it usually means the initial thing, whatever that may be. Last one, and then we'll move on to 3.3. A biologist has a 6,470 gram sample of a radioactive substance. Find the mass of the sample after 7 hours if it is decreasing according to a continuous exponential decay model at a relative rate of 11% per hour. So the fact that it says this continuous exponential decay model right there, that means we're using y equals y sub 0 e to the RT. And as such, we can identify all the bits and pieces. It says find the mass of the sample after 7 hours. So we don't know what y is. Y is the unknown here because y measures the mass at the current time. So y is unknown. Y naught is 6,470 grams. R is the relative rate, which is 11%, which can convert to 0.11. And time is 7 hours. We're going to make our model. In this case, time is going to be measured in hours because that's what it's given as. It's given a relative rate at 11% per hour, so t will be in 7 hours. So we have everything we need to solve for y. Y is equal to y naught 6470 e to the 0. Oh, wait, I made a mistake. And I'm going to go through and we can look at our answer and see why it's wrong. So don't continue writing, but like, so I get this, and then I multiply by 7. And if I plug that into my calculator, 6470 times e raised to the 0.11 times 7, I get 13,973.68. That doesn't make any sense. This is supposed to be decay. How could it grow in size if it's supposed to be decaying? It's supposed to be getting smaller. I made a mistake. R is supposed to be negative. So R equals negative 11%. So it equals negative 0.11. And I'm going to highlight that negative and say because it's a decay model. So the only thing that needs to change is there needs to be a minus sign there. So it should be y equals 6,470 E raised to the negative 0.11 times 7. And if I plug that into my calculator, I get approximately 2,995.69 grams. However, it is clear from the context that we're talking about the measurement of how many grams, the mass of the sample. So if we box our answer saying 2,995.69, we have answered the question in what it's asking. It's asking for grams. So you can write the grams. I'm not going to be too picky about it because it's clear from the context of the problem. But seriously, fight them on it if they ever mark you down. That's ridiculous. It's clear in the problem statements what we're measuring. Cool. Any questions on these? We'll be making them a little more fun right now with our knowledge of exponentials. We can't actually solve for the rate or the time. There's no way to do it yet, but we will in just a moment. So, sorry, I didn't mean to zoom out there. I'm going to move to the next one unless people are still writing. Anybody still writing? Okay. So we go on to 3.3, one of my favorite topics, one of my favorite things to study in mathematics, which are logarithms. Logarithms are a very cool concept, in my opinion. They have some unique properties that you don't see very often in mathematics. So the motivation for logarithms, and this is what mathematicians did when they because exponentials, they kind of make immediate sense to us, right? If you're looking at if you were a biologist back in the 1800s or whatever, you'd be looking at like the population model of like a rabbits or something like that, and you know that it grows exponentially, right? A bunny usually produces, I think, like 9 babies on average, and then those 9 babies have babies, which have 9 babies of themselves, and it just grows exponentially. So that's a natural consequence. So we're used to seeing that, but then if you look at the graph of one of those things, they're 1-to-1. They've passed the horizontal line test. And as such, they must have an inverse function. But what is it? And that is where this comes from. The logarithmic function with base b, I'm going to put the b in quotation marks, for b greater than 0 and b not equal to 1, just for the same reasons about exponential functions. If b is equal to 1, it's not an interesting case. If b is negative, the exponential function isn't defined, so the logarithm wouldn't be defined. And it's denoted y or f of x equals log base b of x. Denoted y equals log base b of x. That's how you say it out loud. The logarithmic function with base b is y equals log base b of x. And it's defined, this is a new thing that we'll see somewhat happen, especially when we get into trig and you talk about inverse trig. It's defined recursively, which means that it's defined from the previous thing. So y equals log base b of x happens if and only if b to the y is equal to x. So in order to know how a logarithm works at first, you kind of have to describe it in terms of an exponential function. That's at least at first. You start to realize how to work with them later on once we learn their properties and things like that. But for now, that's how it's defined. Y equals b log base b of x if and only if when you plug in y into the base, you get back the inside of the logarithm. We call the left-hand side logarithmic form. And we call the right-hand side exponential form. So the cool thing here then is that means that any really equation we can write, we can sometimes write it in exponential form, which means we can convert it backwards and forwards between logarithmic and exponential form. So a couple notes about logarithms. The first thing is that logarithmic functions and exponential functions, they are inverses of each other. And so that means they cancel each other out. Like when you multiply 2 and 1/2, they cancel each other out. And so here, what that looks like is b, oh, wrong color, b raised to the log base b of x equals x. And log base b of b raised to the x is equal to x. But this can be generalized. It doesn't have to just be an x there. That's just showing you how they're exactly inverses, inverse functions, but they cancel each other out. So you can have anything inside that x and it works. So in particular, what I like to write is I like to write b to the log base b of a blue box is just equal to the blue box. So the b and the log base b cancel each other out. And so you can write this. I didn't want it getting too muddy, but basically the log base b and the b cancel. And similarly, if you have log base b of b to the red triangle, that just equals the red triangle. So like right here, once again, the b and the log base b cancel. That's what's going on. They're inverses of each other, just like 1 and 1/2 when you multiply them together, or 2 and -2 when you add them together. They cancel each other out. Yes, JT.
So it's the log base b is like one specific thing.
Mm-hmm.
If I would have thought like the b in front of the log, it would cancel out the b. So it's just anytime it cancels, the log cancels too.
Yes. So log base b is what is like is the other portion of it. It's like a square root symbol, right? It's a whole thing. Like the log base, like if you don't write it, I mean, we'll see in a second that you can write log, but it means this very, very specific thing. But log base b is that whole entity. So an interesting perspective, though it's not super useful, is that with exponential functions, the input is an exponent and the output is a number. But what happens with logarithms is because it's the inverse, it goes in the reverse direction. Their input is a number and it spits out an exponent. And as such, logarithms grow very, 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 very slowly. And we'll see that when we look at their graphs. Now, if you were me growing up, I just had to learn this by brute force. I didn't learn about this trick until I was in grad school when one of my students in math, essentially math 126, showed me it. I was like, that's a beautiful trick, and I'm stealing that. And it made it so much easier for all of my students. So there's a quick remembering trick to convert between logarithmic and exponential form. So leave a little bit of space up. Well, we'll write the statement. Start, unquote, start at the base, move across the equal sign, and back over. I'll show you what I mean once we get to it, once you've read that down. Start at the base, work your way across the equal sign, and then back over it. What does that mean? So if we have log y equals log base b of x, and we want to go from logarithmic to exponential form. So I'm going to do this cool double arrow thing. The red means it's going to the right, going in the right direction. The blue means it's going from the right backwards to the left. So to convert between logarithmic, to go from logarithmic form to exponential form, start at the base, work your way across the equal sign, and then back over. And so we get b to the y equals x. So once we've drawn it, I'm going to reiterate it because so you can see how I drew it. And the same is true. The great thing is this works backwards and forwards. You start with the base, work your way across the equal sign, and then back over. So going backwards, log base b of x is equal to y. Start with the base because that's the base, that's the foundation, right? Logarithmic functions and exponential functions, at their core, they are defined by their b value, by their base. So that's a good memory thing. You have to start with the base because of course you do. You move your way across the equal sign. So going from logarithmic to exponential, start with the base, work your way across the equal sign, and then back over. B to the y equals x. Or in vice versa, log base b of x equals y. Start with the base, across the equal sign, back over. That's the memorizing trick. It works really well for me. I've never forgotten it since, but when I used to teach it, I couldn't remember. I had to like refresh on it every day because whenever I taught it, because I did not have a good memorization technique. And then, of course, there are the special bases. Oh yes, JT.
Okay, the B on the blue side,
Mhm.
is that meaning log B?
Log base b, yes. Because remember, it's the logarithm with base b. That's how we define a logarithm. So there's no other thing for this to be. This has to be the base because it's the base of the exponential.
Log.
So because I'm going like, so this is the exponential form. So if I'm given an exponential equation, I can convert it to logarithms by starting with the base and going log base b of x is equal to y. That's what's going on. The special bases, there is the natural base, log base e. And so log base e is denoted ln. This is the natural log. So I hate to do this. It sucks that we have to know the name of it, but the reason for this is once again mathematicians being very, very lazy. We hate to write things if we don't have to. And because the natural log is so commonly used, we didn't want to keep writing log base e of blank. We wanted to make it easier to read, so we made up a notation. We wrote it as ln. That's the best explanation I can think of as to why we write our own. It has its own name. And key thing there, that is ln. If you're looking on Alex, it looks like it's in. And I get this. I have my online students in 126. I even mentioned it during the video, but they still like they send me emails saying, Phil, I keep getting the answer wrong. And I keep looking at it, it's like that's an IN. It won't register IN in Alex. It's an LN. LN. Lowercase L, lowercase n. And then base 10, and that's going to say that log base 10 is denoted log with no base. And that's the common log. Common log because it's base 10. It's our decimal system. That's why it's the common log, because it's useful in those contexts. A lot of things can be broken down into our decimal system. So that's why it would be called the common log. And because it also gets used quite frequently, that's why we have it being abbreviated. We save ourselves 2 pen strokes overall. So that's why it's useful. Any questions on that? All right, so we're going to convert between logarithmic and exponential form several times. So we're going to go from one form to the other or vice versa. So we're starting with the logarithmic form in part A. So to convert it back, start with the base, work your way across the equal sign, and then back over. So the exponential form would be 2 to the 3 is equal to 8. Start with the base, across the equal sign, then back over. 2 to the 3 is equal to 8. Yes, JT.
Okay, so when you move the base, like to the left.
Mhm.
over, it bumps whatever was at that base up to like an exponent spot.
Yeah, to a base of an exponential function. Yes.
Okay.
Log of x equals 7. That's the common log. So there's an implied 10 because it's the common log. So start at the base, work your way across the equal sign, and then back over. So 10 to the 7 equals x. The next one, 64 equals 8 squared. So to convert it to exponential form, you start with the base, always start with the base, work your way across the equal sign, and then back over. So it's going to be log base 8 of 64 is equal to 2. Yes.
I guess I'm starting. Why is there an arrow that goes back?
Over?
64, yeah, over, because isn't it not going anywhere?
Well, so in short, it's that the logarithm should produce the exponent. So exponential functions, they take a number, they take in an exponent, spit out a number. Logarithms take in the number and spit out the exponent. So in the to introduce it, the exponent is here. It should be on the other side because logarithms spit out the exponents. But the remembering trick is just like it's just that it's a way to memorize it, kind of like PEMDAS, right? So the reason it does that is because it does. Essentially, it has to be that way for the memorization trick to work. Start with the base, work your way across the equal sign, and then back over to the exponent.
Saying back over is just meaning that's where they hit.
Yes. So like it's log base 8 of 64 is equal to 2.
Okay.
That's how it works. ln of y, that is log base e. So there's an e here. So start with the base, work your way across the equal sign, and then back over. So we have e to the -5 is equal to y. Now, this might seem stupid, by the way. This might seem like, why are we doing this? Why are we converting between exponential and logarithmic form? This seems like a really silly, unnecessary thing. However, this will allow us to solve logarithmic and exponential equations soon enough. There's a valid reason to study this part. All right. I want you to do E and F. Oh, go ahead, JT.
Sorry. Would you be wrong then to put the ln with the -5 as its exponent instead of e?
What do you mean?
Like if ln just means like log e, right?
Mm-hmm.
If you just wrote ln and then where the e is instead, you like move the form.
Like writing it, so writing the purple that I wrote, like that, or writing it over here.
So like writing it over there.
So yeah, like when you convert from logarithmic to exponential form, the logarithm converts to an exponent. So the logarithm goes away. No. Good question. This is a new thing. We haven't seen this before. Logarithms are a strange concept at first. For this one, we'll start at the base, which is 1/4 here. Move your way across the equal sign and then back over. So it's log base 1/4 of 6 is equal to x. These other, sorry, F and G, I wanted to go through together. I'm sorry, we haven't really been able to do any by ourselves. But this one, 7 equals 10 to the W. To convert it to logarithmic form, start at the base, work your way across the equal sign, and then back over. So it's going to be log base 10 of 7 equals W, but this is the common log. So it really should be written log of 7 equals W. Now, on an exam, would I really have a problem with that? No. If you wrote log base 10, I probably wouldn't have a problem. I just correct you. I do the caramel macchiato thing. If you say caramel macchiato to a Starbucks barista, let's say caramel macchiato. They'll correct you, but they're not going to get mad at you for not knowing it, hypothetically, unless they're a coffee aficionado. Well, in which case, that's a person you don't need in your life. So, similar situation with the next one. E to the 2t is equal to 5. Start with the base, work your way across the equal sign, and then back over. And so this becomes log base E of 5 is equal to 2t, which this is the natural log. So we should write it as ln of 5 is equal to 2t. And last but not least, log base 6 of the quantity 3y plus 1 is equal to -2. No one said it had to be a singular entity, like a monomial. It could be multiple things. It could be a really long expression on the inside of the logarithm, but it still follows the same pattern. Start with the base, work your way across the equal sign, and then back over. So it's 6 raised to the -2 is equal to 3y plus 1. The way I like to think about these, by the way, I know they look weird at first, but just imagine it like you're learning how to play with a new type of Lego. Like you're given one of those cool Lego sets that has like something you've never really seen before. They get you to introduce those cool pieces, and now you have to working with a new piece. It's like, oh, that's how that works. Okay. My son was working with those little washers that you put on like the cross bars, and he never worked with those before, so he was struggling with it at first. But once he got around to it, he started working, and he totally got it. But they're just Legos, really. They are. I know it doesn't sound like it, but once you see 3.4, you'll start to see where that comes from. So unless there's any questions on converting between logarithmic and exponential form. Totally fine if there are. A useful exponent rule, and I could prove it if you'd like, maybe during the break or something, but it says that if a to the u is equal to a to the v, then u is equal to v. And that's a true statement. So if you have two exponentials, a to the u and a to the v, and they're equal to each other, the only way that they could be is if the exponents are equal to each other, because a is a fixed number. And I hope that is intuitive, right? If you have two things equal to each other and a is fixed, it's just some number. It could be 5, could be 3,000, doesn't matter. If they're both equal, there's no other way for that thing to be equal unless their exponents are equal. And so that's where we'll do how we'll use this. I think this will probably be a good time for a break. So let's come back at about 10:08. 10:09. Let's do 10:09. And we'll come back at that point. People watch the recording, do some guided meditation or whatever you need to do. And we're back. So we're going to work through this one. So now, this is an outdated thing, and I hate that we have to deal with it. It's a fun process. It's a fun mental technique, but if this problem shows up on a quiz or an exam, I'm not going to stop you if you use your calculator to figure it out, right? Like you can literally use the calculator to do it. The answer to this one is going to be 3. But let's see that this will play a role soon. This will play a role as a little clever trick that we can do. So it is good practice. So we don't know what this number is. So we don't know what this is. We'll call it y. If we don't know what it is, we'll call it y. You could call it x. You could call it a puppy, whatever you really want to do. And so what we can do, therefore, is we can convert it to exponential form. So we can start with the base, work our way across the equal sign, and then back over to say that 4 to the y is equal to 64. Now, at first glance, it doesn't make much sense, but 64 is relatable to 4 because 4 cubed is 64. This is 4 cubed. So we have 4 to the y equaling 4 cubed, and that means that y is equal to 3. From the above statement, if you have a to the u equals a to the v, in this case, 4 to the y equals 4 to the 3, then the exponents are equal to each other. So y is equal to 3, and that is log base 4 of 64 is equal to 3. Sure, I'll use an oval. Yes, JT.
This might be common knowledge, but can you teach us how to do that in a calculator, like how to solve it?
Yes. So I'm going to pause the recording. People watching the recording, you can email me and I can show you, or talk to me before class or something and I can show you. So this is a very, very outdated thing. It used to be useful because back in the day, our calculators couldn't do this. And so we had to think of clever ways to figure them out. But nowadays, it's much easier. So it's kind of an outdated thing. It just has a useful little technique that we will see in a moment. So this time, let's call it, what do you guys want? What letter? Capital or lowercase? I don't care. Capital Q. So start with the base, work your way across the equal sign and then back over. We have 5 to the q equals 1/25. And then if you remember our exponent rules, 1 over 25, that's 1 over 5 squared, which is equal to 5 to the negative 2. So that means that 5 to the q is equal to 5 to the negative 2, which means that q, which is our value in question, is equal to negative 2. The only thing I'm going to, so I'm going to just let us use our calculator to find the next one. So using calculator, this will equal 5. Because 10,000 or 100,000 is 10 to the 5th. Yes.
What do you put for the, like, when it's just log?
Then that's the common logarithm, and there should be a button for that. It's usually right next to ln.
Oh,
Yes. So you can use your calculator to do these ones. It really is not a big problem. The next one, if you plug it into your calculator, you get exactly 0. And we can understand why that's the case in just a moment. But ln of 0, go ahead and try and plug that into your calculator. What do you get? Domain error, math error, yes. So the reason for that is that this is not solvable. So this is a trick question. Let's assume that it was equal to y. Then there's an implied log base e. And so we'd be saying e to the y is equal to 0, right? That's with, like, if we were to convert that to exponential form, we would say that start with the base e to the y is equal to 0. But we learned last time with exponential functions, this is not possible. because e to the y is strictly greater than 0 for any y. Any exponential function is never 0. It's always positive. Any one of the parent exponential functions, that is never 0. And that brings up a very valid point, which we'll see in just a moment, about logarithms. Any questions on these? So please feel free to use your calculator. Yes.
Would this be like an actual question?
On the test, I probably won't. I'd rather ask you to convert it from exponential to logarithmic form. That's a useful thing. But there is going to be this on your on your homework, so might as well get that free part done. The main reason I wanted to bring this up is because of this useful fact that if you have a base of something equals the same base of something else, then the exponents have to be equal to each other. So, graphs of logarithms. Since 2 to the x and log base 2 of x are inverse of each other, we know that what the graph of f should look like from unit, and we know what the graph of f should look like. We can use our knowledge of inverse functions to figure out what the graph of the logarithm is. In particular, please remember that if a comma b is on f, that happens if and only if b comma a is on f inverse. So since the exponential function y to the equals 2 to the x has the points -1 comma 1/2, 0 comma 1, and 1 comma 2, the logarithm has the points it's called 1/2 comma -1, 1 comma 0, and 2 comma 1. So we'll go ahead and plot those points. I'm going to write this one in orange. I don't know why, but I'm going to do that. So 1/2 comma -1 is right there. 1 comma 0 is right there. And then 2 comma 1 is right there. And in fact, what you'll see, just like with the exponential function, whenever you plug in a more and more negative number, right? So if I plug in -2, I'm going to get 1/4. So I have the point 1/4 comma -2. If I plug in -3, I get 1/8 in the exponential function. So I'd have I have 1/8 comma -3, and so on and so forth. So you'll notice that it never, ever, ever gets to 0. And so what it ends up having is it has a vertical asymptote at x equals 0. And the graph looks roughly like this, which is the reflected version of e to the x, or of 2 to the x. It's the reflected version across the line y equals x. So with that in mind, we can talk about the properties of the logarithmic functions. And so remember about inverse functions. The domain of a function is equal to the range of its inverse. And the range of the function is equal to the domain of the inverse, and vice versa. So the domain of this is equal to the range of the exponential function, which we saw was 0 to positive infinity. And the range will be negative infinity to positive infinity. Key point from the domain, this means the inside of a log needs to be positive. The important points for a logarithm is that f of 1 is always equal to 0 for any base. So log base b of 1 is always 0. And then log base b of b is equal to 1. So we have the points, the important points, 1 comma 0 and b comma 1. And then it has a vertical asymptote at x equals 0. Yeah. And so these are what the graphs look like. They have the point 1 comma 0 and b comma 1, except for the case when b is between 0 and 1. And so the thing is, this case, is so rare, Gordon Ramsay won't serve it. Solid joke right there. It's wrong. It's very, very rare. I count on 0 hands the number of times I've had to use a log base 1/4 or log base 2/3. So I don't think it'll ever show up in your homework, and if it does, let me know, and I'll bypass it. I can promise you though, on the exam, there will never be a base between 0 and 1. It just never happens. It's just so rare that it never should happen. Okay. In typical, like we'll work with b to b greater than 1. And so you look at that curve, and it looks like it's kind of leveling off, but it's not. It's one of the slowest growing functions known to man. So, case in point, if you go with let's just look at log base 10s, the common logarithm. So at 1, it's 0. At 10, it equals 1. So I have to go 9 more units just to go up 1 unit in x value or in y value. And then log of 100 is 2. So I have to go an additional 90 just to go up 1 y value. And then if I plug in log of 1,000, that's equal to 3. So I have to go 900 more from that just to go up 1. And then 10,000 will go up to 4. So it takes another 9,000 to get up to another point. So it grows incredibly slow. Logarithms are one of the slowest growing functions. They do increase indefinitely, and they will eventually reach infinity, but it takes very, very long for them to do so. So let's go ahead and graph one of them. But of course, you can also plot points. So we'll do it with RCS at first. We'll do it with a linear transformation, and then we'll do it without in just a moment. So log base 4, the parent, log base 5 of x plus 4 minus 2, the parent graph is y equals log base 5 of x. So that has the points 1, 0 and 5, 1, and has a vertical asymptote through x equals 0. The point 1, 0 and 5, 1, and it should look roughly like that. Yes. No worries. How did I get those points?
Yeah.
Those are guaranteed points on any function. So a logarithm will always have the point, like the parent logarithms, that is, they will always have the point 1, 0, and they will always have the point b, 1, base, 1. So in this case, since it's base 5, we have 5, 1. If that was log base 6, we'd have 6, 1. If it was log base 2, we'd have 2, 1, and so on and so forth. So this one, there's no negative x. So if we're following RCS, we can skip that first step. There are no reflections. There are no compressions or stretches, but there's a shift left 4 and down 2. So we'll take that point, 1, 0, or 1, 0. We'll shift it left 4, 1, 2, 3, 4, and down 2 to the point -3, -2. And then we'll take the point 5, 1, move it left 4, so 1, 2, 3, 4, and then down 2, 1, 2, to the point 1, -1. So now that we've plotted those things, now that we've got those things, we'll plot them, -3, -2, and -1, 1. But the question is, where is the vertical asymptote? Notice that we didn't stretch this graph at all. We didn't stretch it vertically or horizontally or anything like that. So we just moved it left and right, left and down. -4, because in the original parent graph, it's just 1 to the left of that point. So it should be 1 to the left of that point. So we'll write our vertical asymptote right at x equals 4. And so the graph of this logarithm will look roughly like this. Doesn't need to be perfect, but it looks like that. So there's a key thing I wanted to notice. Is it moved? So like for exponential functions, the horizontal asymptote that they had moved with vertical shifts. And by a similar argument, the VA travels with horizontal shifts. So the domain here, by looking at the graph, it's parenthesis -4 to positive infinity. Its range is negative infinity to positive infinity, and its VA is at x equals -4. So we can do it. So that's one way to do it. And so just to give you the intuition as to why that's true, why the vertical asymptote travels with the horizontal shifts, is imagine if I move this up or down, nothing really happens to that vertical asymptote. It stays on the y-axis. But as soon as I start shifting it left or shifting it right, it travels along with it. If I were to vertically stretch it, I can't do it with this type of technology. But if I were to like take it on silly putty and just stretch it, the y-axis, that vertical asymptote would stay where it is. And even still, if I were to try and horizontally stretch it, it's on the line y equals 0 or x equals 0. So it's already on the y-axis. So stretching it wouldn't really do anything. It wouldn't double its y value or x value. It would just keep it the same. So it's only with the with the horizontal shifts that it changes. So this is the next one, and we'll do this one. So this is 1 minus 2 log base 3 of x, which I'm just going to rewrite. Well, actually, I'm not going to rewrite. Oh, yeah, I am going to rewrite. Is equal to -2 log base 3 of x plus 1. And so there's no horizontal shift. So VA stays at x equals 0. The vertical asymptotes will only move if they have a vertical or horizontal shift. Yes.
So B is always gonna be at x equals 0 unless there's a shift.
Yes, unless that was x plus 5 on the inside or x minus 3 on the inside, it'll stay at x equals 0. So we'll go ahead and graph it. Just right now, like we'll get that out of the way. And so what I'm going to say now is could plot points instead of linear transformations. So, and in this case, if you're using this on Alex or whatever, you're going to want to do the same thing we do with exponential functions is write the approximation. Write the exact form instead of the approximation when you're plugging it in to plot the points. But when we're drawing it with our caveman hand, we have to use the approximations. So, for example, if I do f of 1, let's just use that for best guess. F of 1 would equal 1 minus 2, or I mean, we can write it in myriad of ways. I rewrote it as -2. So -2 log base 3 of 1 plus 1, and that will equal 1. So we have the point 1 comma 1. We lucked out. That's a nice exact point that we don't need to worry about like plugging in logs or whatever to get it to be right. So we have that 1 point right here. And then let's just do f of 2. And that'll be -2 log base 3 of 2 plus 1. So, which is approximately -0.26. So you have the point 2 comma -2 log base 3 of 2 plus 1, which is approximately 2 comma -0.26. I'm writing that quickly, so I'm going to slow down for a second. So we'll plot that point. So 2 comma negative 0.26 is roughly about there. It doesn't need to be perfect. Now, this is where you might want to plug in an extra point or two to further verify it to yourself of how the graph is going to look. But if you remember your your linear transformations, this has a -2, a negative sign out here. It's on the outside, so that it affects the y stuff. So this is a reflection across the x-axis. So it should look like this, but you can always plot a couple extra points to be certain. That. Yes, JT.
So if, when we do like the F2, like going to get points, are you just putting that in your calculator?
Yes, yes.
Okay.
So I have the exact form, -2 log base 3 of 2 plus 1. That's a number, and that's the exact form because log base 3 of 2 is an irrational number. But then every once in a while, if you want to, the clever thing is to choose powers of the base. Try and make the inside a power of the base. So we want to do like 9 or something like that, or 27 or something like that, because that will give us a nice logarithm value. But that's besides the point. Just plot the approximation is fine. F is equal to -x plus 4. I'm going to start this one off for us. The thing is, because it's a negative x, we want to factor it. Lin transformations implies or tells us to factor out a -1. So it should be f of x equals natural log of the quantity negative parentheses x plus 4. X minus 4, excuse me. This is that one tricky situation because it's a negative x that we have to factor out that because that changes how the shift is. Because it's -x plus 4, it's not a shift to the right. All right, so it's not a shift to the left, it's a shift to the right. Because it's a minus on the inside, so it's a shift right 4, which implies the VA is at x equals 4. So I'll let you go ahead and plug in things. So you don't. Oh, good. Go ahead, JT.
When you factor out the negative, does that mean it's a reflection?
Yes, it is. It is a reflection across the y-axis based on 1.6's knowledge. And so instead of going over here, it should be over here because it's going to be a reflection. Now, that being said, you could just plug in values. If you try and do natural log of, like if you plug in 6, you'll see that you get domain error. You see that you get a math error. So keep trying more and more values to the right of it, and you'll keep getting a domain error. So then you need to try ones to the left of it. And you should find some values. So let's see, f of 5 equals natural log of -1, which doesn't exist. So we'll check x values on the left. F of 3 is natural log of 1, which is 0. So we have the point 3 comma 0. And then we'll do f of 2, which would be natural log of 2, which is approximately 0.69. So we have the point 2 comma natural log of 2, which is approximately 2 comma 0.69. I'm sorry, I wrote that very quickly, so let me slow down. Why's my mouse there? Why's my mouse pointer there? So I'm just picking up random values. There's no rhyme or reason to it. You could have chosen f of 0. You could have chosen f of -5. It doesn't matter. But the actual exact point when you plug in 2 will be 2 comma natural log of 2. But drawing it with our caveman hand, we'll use 2 comma 0.69, which is approximately right about there. And so our graph should look roughly like this, but you can always use more points to further grasp it for you. And I didn't write the domains of the ranges or whatever. Just didn't feel like it. Wouldn't that be nice if you could just do that on the exam? I don't feel like answering that problem. Yeah, JT.
So when you're putting it in parentheses, like if I were to input them in Alex, would I put, like, I guess where the X is, and then like
The x coordinate.
parentheses inside of the parentheses? Yeah, do you just solve it and then put that in, or do you put the full equation like that's?
So don't worry about, like, just plug it in exactly as you see it. So when you plug it into your value, you get natural log of 2. So right, your x coordinate is 2, comma, your y coordinate would be natural log of 2. Does that answer your question? Or no?
I just meant like, if it's natural log, parentheses, negative, parentheses, and then you put in like the, whatever, the f of 2, so you put in the 2 minus 4, like, do you leave that full equation, or you solve it and just put natural log of whatever the answer is?
Natural log of whatever the simplified value is, but it'll handle it. It'll handle it if you write natural log of -2 minus 4. It will handle it. All right. So the domains for this first one, I forgot to write it, but it's 0 to positive infinity, and its range is -infinity to positive infinity with a VA at x equals 0. And the second one has a domain of -infinity to +4, a range of -infinity to positive infinity, even though it doesn't look like it, and a VA at x equals 4. So that's how you can graph them. Yay, new thing that we can do. Very, very fun, very cool thing to bust out at parties, I know. But I'd rather be more interested in how to use them. So one of the cool things that happens, especially in later on, is you'll deal with logarithmic functions and finding their derivatives, but sometimes you need to make sure you know where you're defined for your domain. So as we saw earlier, the domain of a logarithm is 0 to positive infinity. So a generalization of this, and this is the important part, is the domain of f of x equals log base b of a blue box is found by solving blue box is greater than 0. Put that down and we'll explain what's going on here. This is new. Yes, it is new. Absolutely. That's not like that's not surprising because it's a new concept. However, it's the same process. When we were asked to find the domain of a radical for a square root function, right? We made the inside greater than or equal to 0 because we know that the even roots, specifically square root, can only be defined in the real numbers for values 0 or larger. So if I'm asked to find the domain of a logarithm, logarithms can only take in positive numbers. They can't take in 0. They can't take in negative numbers. So to find the logarithms domain, you just need to set the inside greater than or equal greater than 0 strictly. So, for example, this one right here, find the domain of it. So yes, this is new, but it's not really. It's still applying the same kind of terminology. The domain is where the function is defined. Logarithms are only defined for values greater than 0, so the inside of the logarithm needs to be positive. For example, if we're trying to find the domain of f of x equals log base 5 of 4x minus 7, it doesn't matter what the base is. The only thing that's important is that the inside of a logarithm needs to be greater than 0. We need this greater than 0. So we have to solve 4x minus 7 is greater than 0. That gives us x needs to be greater than 7/4, because we'll add 7 and then divide by 4. And so on a number line, we could draw it, but just in the interest of time, this is 7/4 to positive infinity. Yeah, the inside. I'm sure it has its own name, just like the inside of a radical is called the radicand. I'm sure it has a stupid name that is meant to try and scare people away from it and try and make it elitist. But yeah, the inside. It doesn't matter what type of logarithm it is. They all have the same defining characteristic, is that logarithms can only plug in positive numbers. They can't plug in negative or 0. So that's why it's strictly greater than 0. And this next one, super fun one. Love it. Awesome problem. H of x is equal to natural log of x to the 4th plus 9x cubed minus 10x squared. We need the inside. We need x to the 4th plus 9x cubed minus 10x squared greater than 0. And we know what that is, right? It's a nonlinear inequality. We love ourselves a good old nonlinear inequality, right? You got to factor it, find the VIPs, so on and so forth. This factors to x squared times x squared plus 9x minus 10 is greater than 0. And that will factor nicely to x squared times parentheses x minus 1 times parentheses x plus 10 is greater than 0. And I'll let you guys finish the rest of that one. I'll give you the answer. ... A miracle occurs and you get the answer, which is negative infinity to negative 10 union 1 to positive infinity. Legitimately on my chemistry, my organic chemistry exam, on the final exam, it was so hard. I think I've said this part, that one of the students behind me started crying, which is always a fun thing to hear during a final exams, to hear someone having a mental breakdown. That's never fun to hear. But in addition, the problem that I was looking at, I had no idea how to convert one compound to the other. And so I did what my mom told me to do, and I just wrote arrow, a magic arrow, and then I wrote the compound, because I had no idea how to solve it. And so maybe you could do that magic and you get the answer. So you got to make a sign chart, have a fun old time. It'll be a grand old time. Right? So last thing for logarithms. So I think we're going to start up 3.4 next time. But we'll get to that. And I think what's going to end up happening, so 3.4 is properties of logarithms, 3.5 is logarithmic equations, and then 3.6 is applications. Now, looking at the calendar, I have a hinting suspicion that we are not going to be able to get to 3.6 until Wednesday Tuesday of next week, or at least start it on Monday, finish it on Tuesday, and have the rest of the time for review. So I am probably going to make the executive decision right now that applications of logarithmic and exponential equations will not be on our exam 3. Big bummer, right? We don't have to do any word problems. That shucks, right? Aw, fiddlesticks. We don't have to do any application problems. There might be one on the final exam. Who's to say? Let's just pray, right? I don't want to do them either. I don't want to grade that. It's never a fun problem to grade. So let's just hope that the powers that be in the department have decided, and let's give them a break this spring and not put an an application problem. Could be, never know. Okay, so we can find inverses. So now that we know about the connection between logarithms and inverses, we can find inverse functions, logarithms and exponentials, excuse me. And so the key is the remembering trick. That is to say, y equals log base b of x. Start with the base, work your way across the equal sign and then back over to give you b to the y is equal to x. And then you can work backwards in the same fashion. Start with the base, move your way across the equal sign and then back over. Log base b of x is equal to y, and we're all good. So see how that gets used here. We'll probably do A and then we'll finish off B tomorrow. So we might we're gonna have to move some homework around, I think. Maybe. Yeah, big bummer as well. Can I get a fiddlesticks? All right. That's actually pretty good imitation of it. You need a little more vocal, but then Patrick's class would probably be like, what's going on? My ex-department chair. It's a nice guy. Well, we replace him every 2 years. We cycle through it in the department. So, don't vote him off the island, but every year we get like every 3 years we get a new election and we let someone else do the job, which is a really bad concept because then like you go from being a colleague to being the head, and so like if you had a really good relationship with one person, now like you have to be a boss, and so like yeah, you don't really do much now. I have to actually get on your case about it. Anyways, I'm getting sidetracked. That one's your guys' fault. So this is y equals 10 to the 3x minus 7. So inverse functions, to find them, you replace your f with a y, and then you have to solve for x. So we want to get that 3x by itself. Naturally, then we would have to add 7 and get that y plus 7 is equal to 10 to the 3x. And so we're like, okay, well, how do I solve for x? I use the remembering trick. I convert this to exponential to logarithmic form. Start with the base, work your way across the equal sign, and then back over. So we get that log base 10, which is the common log, we'll replace it in just a moment, of y plus 7 is equal to 3x. Last step is to divide both sides by 3. To get the x by itself, we get x is equal to log of y plus 7. I'll make a mention of that too. This is the common log. Divided by 3. And then we have our final answer once we convert it. Like once we solve for x, we flip-flop the x and the y's and write it as an f inverse function. So this finally becomes f inverse of x is equal to log of x plus 7 divided by 3. Yes, JT.
The log does get divided by whatever.
Yeah, because the logarithm is its own unit of something, and then we're going to divide that entire thing by 3. That's what we get. Yes, JT.
So how you do the, it's called, like the 10 over and output over.
My student called it the curly Q. I don't know why, but
I like that. So can you do that at any point of it, or was there like a specific timing when you had to do it?
so I had to do it now because I needed to get the exponential by itself.
Oh,
Because if the 7 is on the other side, then I can't do it because it's not something equals an exponential.
Okay.
So yeah, that's why I had to add 7 first to get the exponential by itself. We'll go over that one again and go over part B tomorrow. If you want to try that one on your own time, the answer is that k inverse of x is equal to 24 to the x minus 4 plus 2. You can take a picture of that if you want. but we'll go over it next time. So if you guys have any questions, feel free to email me. Remember that your redo is your exam 1 redo, not the exam 2 redo, but the exam 1 redo is due this tomorrow. You can always email me questions about it. Sorry if you emailed me on Monday or on Sunday or whatever, and I haven't gotten back to it. I have been swamped, but I will get back to it as soon as possible. So yeah, if you have any questions, email me. Otherwise, have a great rest of your day, and we'll see you then.